My name is Antonio Galves. In this third lesson, I will present to you a case study. We have two goals in this lesson. One is to discuss how to deal with a real scientific or technological problem, and therefore deal with real data, with a finite sample of real data. The other goal is to present a new criterion for context-free model selection, namely the smallest maximizer criterion, which was introduced and developed to deal with the data to be discussed here, but we believe this criterion is interesting by itself. So let's start by presenting the problem we wanted to address and motivate everything. So this is a linguistic question. You have two questions to be addressed in this linguistic question. The first one is whether there exist rhythmic patterns characterizing and distinguishing between Brazilian and European Portuguese. Henceforth, I will call BP and EP. Second question is whether it's possible to identify these patterns if we just look to written texts in BP and EP. Attention, we're not interested to discuss the difference between Brazilian and European Portuguese syntax. This is an important and well-known problem, but this is not our goal here. Our goal here is to discuss if the successive choices of words by speakers of Brazilian and European Portuguese reveal different stress patterns preferences. Oh, it's natural to ask if this is really a relevant technological issue, as I told you. I will let you find the answer to this question, but I give you two hints. The first hint is, think about the design of algorithms of text-to-speech synthesis. So the goal of such an algorithm is to produce acoustic signal reading in a natural way, in a realistic way, a written text. There is also the inverse problem. You have recorded a native speaker of Brazilian Portuguese, of European Portuguese, or more generally, a native speaker of a certain region, and you want to identify the region in which this person learned his mother tongue language. So in both cases, the identification of intonational and rhythmic patterns play a crucial role. If you want to design a text-to-speech algorithm which is able to produce acoustic signal which looks like someone speaking such a particular language, you must present this acoustic signal with correct rhythmic patterns. And inversely, something which distinguishes between speakers of different regions are different ways to address rhythmic questions. So in both questions, which are important technological questions, in both aspects, the identification of rhythmic patterns is very important. This is also an important scientific issue. Actually, a conjecture says that the Brazilian Portuguese and European Portuguese instantiate different rhythmic patterns. And the statistical analysis of samples of acoustic signals obtained by recording native speakers of BP or EP, this analysis of this acoustic signal supports this conjecture. The question is whether we can find these rhythmic patterns distinguishing BP and EP just by looking to written texts in these two languages. If you want to identify rhythmic patterns in the text, the first thing to do is to encode the texts. Encode them in such a way that replace the words by a sequence of labels indicating the basic stress features of this word. The data we analyze is an encoded corpus of newspaper articles. They are editions of the years 94, 95 of the newspaper Folha de São Paulo in Brazil and O Público in Portugal. Now, how do we encode the data? Well, we start by pre-processing the text, where we write compound words, or eliminate, or we write data. This is done in an automatic way. We encode them by assigning one of 4 symbols to each syllable, according to whether the syllable is stressed or not. And here by stress, I mean the main stress of the word. The syllable is the beginning of a prosodic word or not. So there is a difficult word here, prosodic word. By prosodic word, we mean a lexical word like a noun, a verb, together with the functional non-stressed words like articles, prepositions, which precede it. So encoding the data, we have 2 features. Is the syllable stressed or not? Is it the beginning of a prosodic word or not? So we put them together. This we have 0, 0, 1, 0, 0, 1, 1, 1. So we can represent these 2 characteristics, binary characteristic, as with 4 symbols, 0, 1, 2, 3. So 0 stands for non-stressed, non-prosodic word initial syllable. 1 stands to stressed, non-prosodic word initial syllable. 2 to non-stressed, prosodic word initial syllable. And finally, 3 stressed, prosodic word initial syllable. Well, additionally, we add an extra symbol 4 to encode the end of each sentence. Therefore, we remain with 5 symbols, 0, 1, 2, 3, and 4. I give you an example. So, in Portuguese, o menino já comeu o doce. So, o menino is a prosodic word. The first syllable, o, is the first syllable of the prosodic word, but it's not stressed. The second syllable, me, is not the first syllable of the prosodic word, and it's not stressed, so encoded by 0. Ni, it's a stressed syllable, but it's not the initial syllable of the prosodic word, so encoded by 1. And no, again, is neither a stressed syllable nor the initial syllable of the prosodic word, so encoded by 0. Já. Já is the first syllable of a prosodic word, and it is a stressed syllable, so encode it by 3. Comeu. Co is the first syllable of the prosodic word, but it's not stressed, encode it by 2. Meu, it's not the first syllable, but it is a stressed syllable, so encode it by 1. O doce. O doce is just a unique prosodic word. O is the first syllable of the prosodic word, but it's not stressed. Do, it's not the first syllable, but it's stressed. 1. Se is not the first syllable, it's not stressed. 0. And then I have a dot, the end of the sentence, and encode it with 4. We started with written text. We encoded this written text, replacing every syllable by one of the symbols 0, 1, 2, or 3, and replace also the dots represents the end of a sentence by symbol 4. And now we consider this sequence of rhythmic labels as a sample generated by a stochastic chain with memory of variable length. And you want to identify the context tree we generate this sample. So we're looking for the smallest context tree, which maximizes the probability of occurrence of this sample. The idea behind this approach is that the sequence of context occurring in the sample identifies somehow the rhythmic domains structuring the sequences of rhythmic labels. So this is an idea which appears in biology and linguistics, in many scientific domains, that strings of amino acids or DNA bases or rhythmic features, they have a structure which is based in domains. So it's natural to conjecture that these domains, in this case, the rhythmic domains, are constituted by context. So it's just natural to represent the whole sequence of rhythmic labels as a sample generated by a context tree model to see if the context which will appear at each step will give you a hint about the rhythmic domains which are behind. Well, the good news is that the statistical analysis we performed on the encoded newspaper text supported this conjecture. But before getting there, we have some job to do. Selecting a context tree for the sample of encoded data. We have already seen in these lectures that there is a criterion, the Bayesian information criterion, which selects in a consistent way the context tree which best fits a data sample. I remember to you, the BIC with penalizing constant selects a tree tau hat BIC, which depends on the sample on the constant as the tree which maximizes this balance between the logarithm of the likelihood of the sample with 3 tau minus, that's the balance, the number of degrees of freedom of the tree times logarithm of the size of the sample. And in front of this term, we have the penalizing constant, which is more or less the price we must pay for every extra element we put in the model. So we look for the tree which maximizes balance. So I remember to you, in this formula, Tn is a set of candidate trees compatible with the sequence. And df tau is the number of degrees of freedom, number of parameters associated to the tree tau. We know that the Bayesian information criterion is a consistent procedure, but there is a problem, and this is a central question maybe we want to discuss in this lesson. Remember, Chiesa and Talada, in a remarkable paper, proved the asymptotic consistency of the BIC for context tree models for any value of the penalizing constant C. This means that the choice we make for the penalizing constant C is relevant if the sample is infinitely large. In the tradition of the Bayesian tradition, the constant C is equal 1/2. But now, in real life, samples are always finite. They can be very big, but they are finite. And therefore, in the balance we have here, the specific value of C affects the choice. How can we choose C? And that was a situation in which we found ourselves, the authors of this paper, context tree selection and linguistic retrieval from written texts. How to choose the penalty constant to apply the BIC? For finite samples, the choice of the penalty constant C does matter. Actually, the choice depends crucially on the value of the penalizing constant. How to choose this constant? We had a conjecture concerning the context trees that should better fit the BP and the EP encoded samples, respectively. Actually, there was a choice of the penalty constant C for which the BIC balance with the BP data was maximized by the context tree, which was conjectured to be the correct one in the BP case, and the same occurred in the EP case. But unfortunately, this constant differ in the BP and the EP case. How to choose C? Well, it turns out that this is a central question if we need to analyze real-life data. This is a central question for data scientists. And this maybe is one of the messages I want to pass to you in this lesson. So at this point, we had an epiphany. It was one of the moments in my life is suddenly we saw something which is very surprising. So let me tell you what we did. We want to understand the influence of the penalizing constant on the BIC balance and on the choice of the tree which maximizes the balance with this value of C. So we decided to compute the maximized BIC tree for different values of the penalizing constant. We did it for EP and BP data. Observe that the function which assigns a tree to each value of the penalizing constant is a step function, because for an interval of values in C, the tree does not change. At a certain point, it becomes too expensive to have a certain branch of the tree because the value of C becomes too big, so we decide to cut it. Let us call Cn the image of the function, which associates the tree to each value of the penalizing constant. Let's call champion trees the trees belonging to this set. These are the trees which maximize the likelihood of the sample for if the sample is generated by each one of the champion trees. So we compute the log likelihood of the sample, and the result was surprising. I show to you. That is the result with the BP data. So you see, you have here something which increases in a very steep way, and then it becomes more or less horizontal. It's not horizontal, it's always increasing by convexity reasons, but it is astonishing. Then we decide to do the same for EP data. The result is the same. So at that point, we said, wow, how come? And then an idea appears naturally. I let you think about the idea which occurred to us when you saw these two pictures. That's the epiphany. How to interpret the inflection point? Well, do you have an idea? So In the figure, the vertical axis represents the values of the log likelihood of the sample corresponding to each one of the champion context trees. In the horizontal axis, we indicate the number of leaves of the champion context trees. The champion context trees in the figures are presented in increasing order, starting with the smallest one, the root tree, which corresponds to assume that the data was generated independently. And then we start adding branches to this tree. Now, the conjecture we made, I guess you made it also. We suppose that the inflection point corresponds exactly to the champion context tree that effectively generates the sample. To check this natural idea, we simulated data. So in this case, we know what is the tree which generates the data. So we could see. We generated data. We generate data with this tree, which we will see later, looks like one of the context tree we find. Same alphabet, same number of symbols, more or less. We generate. In this figure, I forgot adding the transition probabilities, but you can find it then in the lecture notes. So using the BIC estimator with different values of C, we obtain trees with one, just a root, 8 leaves, 11, and so on. And the tree with 13 leaves corresponding to the correct tree, the one that you used to simulate that. You see, you have 4, 7, 9, 10, 11, 12, 13. When you plot the log likelihood of the sample as a function of the number of leaves, we see a change of regime as conjectured. So in this figure, unfortunately, the horizontal axis presents not the number of leaves, because this should be 13 leaves, but the index of the tree. Now, let's try to give an heuristic reason for the conjecture. So the conjecture is that the tree which generates the sample will appear here in the inflection point. Let's see if we can explain, give an heuristic reason for this. So the trees presented on the left of the inflection point are smaller than the tree that effectively generates the sample. This means that they don't look enough back in the past to make good predictions about the next step, because they don't have all the branches which is required to make good predictions. They are smaller. So the predictions they are able to do are imprecise, and therefore the likelihood of the sample should be smaller than the likelihood computed using the maximal likelihood estimator associated to the correct context tree. Observe that the likelihood increases when leaves which are effectively pertinent to make good predictions are added to the tree. This explains the steep slope of the log likelihood of the sample corresponding to the champion trees appearing on the left of the inflection point. Recall the notation. X1n is a sample. This is the counting measure. It counts the number of occurrences of the string W in the sample. That's the maximum likelihood estimator associated to the string W. That's the likelihood of the sample with respect to the context tree tau, using the maximum likelihood estimator associated to the contexts in tau. Tn is a set of candidate context tree corresponding to the sample, and tau hat BIC is the context tree selected by using the BIC balance with penalized constant C. Finally, Cn is a set of champion trees. Let's present now our first theorem. The first theorem tells us that the tree generating the sample belongs to the set of champion trees if the sample is large enough. So it's interesting to define an order relation between trees. Tree tau is smaller or equal to tree tau prime if for every context in tau prime there exists a context W in tau, such that W is either equal V or is longer than V. The theorem is the following. Assume X1n is a sample generated by an irreducible stochastic chain with finite context tree tau star. Then Cn is totally ordered with respect to the order, and eventually or more surely tau stars belong to Cn when n diverges. Therefore, if the sample is large enough, the tree generating the sample is a champion tree. Now, okay, that's the first point. So we want to do, we had the conjecture that the tree which generated the sample was the one in which we observed the inflection point. Well, we still don't know this, but it was important to have this tree in the set of champion trees. This is the result we have here. We must continue. We must continue if we want to understand why there is an inflection point exactly in the tree tau star. So in the same conditions as before, a sample generated by a reducible stochastic chain with finite context tree tau star. So if we take a champion tree smaller than tau star, the likelihood associated to tau star is obviously bigger than the likelihood associated to tau, but the difference between them is greater than a constant times the size of the sample. On the other hand, if you have two trees, tau is smaller than tau prime, champion trees, and we have tau greater or equal tau star, which is the correct one, then the difference between the log likelihood associated to tau prime and the log likelihood associated to tau, which is smaller, so it's positive, but it is smaller than a constant times log n. So there is a difference in regime when we goes after the correct champion tree, which is tau star. So this explains the different figures we have in both sides. And this is precisely what we try to explain in words before we prove the theorem. To conclude, the first theorem told us that if the sample is big enough, the tree which generates the sample is one of the champion trees. And this second theorem tells us that before we get to the correct champion tree tau star, the log likelihood increases by an amount which is greater or equal constant times n. But after we cross the tau star, for two trees which are bigger than tau star, so tau star is smaller than tau, that is small is bigger than tau prime, then the difference in log likelihood is bounded above logarithm of n. So this explains the figure. Now, at this point, the question is how to identify the inflection point. And the naive answer is, well, you can do it by visual inspection, maybe. And this is, unfortunately, too naive. Just look at the data. It's not obvious which is the inspection point. Look at the data. You see, I increased a little bit the data, and here we can see in this red circle several points. One of them is the context tree which generates the data in which the inflection point really occur. Which one is the inflection point? So if we increase this picture, this red circle, if we increase it, you have this sequence of points. This is a zoom in the picture. Let's look at the EP case. So again, you have this red region, red circle, red ellipse, and we make a zoom. So which one is the correct one? So visual inspection is not enough, but the theorem, the second theorem gives us the tool we need to identify the inflection point. Let's look at the increment rate. Naive visual inspection is not efficient. Mathematics is required here. And that's the mathematics we need. So we increase by an amount which is greater or equal constant times n before we get to the correct tree. And we increase but by a much smaller rate after we cross the correct tree. So let's consider the class of all champion trees for the infinite sample. So we increase the size of the sample. And the criterion we can use is the following. Look at the difference between the log likelihood for two trees and define the t hat as the smallest tree such that this difference divided by n goes to 0. Oh, why is it so? Because before you increase by more than by at least a constant times n, and after you cross the correct context tree, you increase by less than a constant times log of n. Log of n divided by n, this goes to 0. And so if you define this criterion, we have this theorem. So the probability for infinitely large sample of have t hat different than the correct t star which generated the sample is 0. And we call this criterion the smallest maximizer criterion. But now we could say, okay, this is very nice, but here we are using a limit when n diverges. How do we really identify it when you have a sample which is may be large, but it's finite? Idea. We know that for the champion tree is smaller than the correct tree, the corresponding likelihood increase at least linearly with the size of the sample. We know also that the champion tree bigger than the correct tree, the increment in the corresponding log likelihood increase at most as a logarithm. The question is how to evaluate the rate at which the increment of log likelihood of the sample increases in the sequence of the champion trees. If you have several independent samples generated by the same context tree tau hat, we could estimate the successive increment rates by computing the average across the independent samples, but we don't have this. We just have one sample. How can we estimate the increasing rates? Use a bootstrap procedure. Now we arrive at the conclusion of this lesson. I will explain to you how to use this bootstrap procedure. I start by saying a few words about the bootstrap sampling method. We want to generate a set of independent bootstrap resamples of the original dataset x1n, which is the original string of symbols. To resample, we take advantage of a striking feature which is present in all the champion trees. Namely, the fact that the string with 4 as unique element, this string appears as a context in all the champion trees. So I will quote our paper, tables 5 and 6. So that's the paper, and that's the tables. Table 5. So you see for all the champion trees, 4 is always a context. The same occurs for the EP case. 4 is always a context. So let's use this fact to make the bootstrap resampling. The fact that the string with 4 as unique element appears as a context in all the champion trees means that the successive occurrences of the symbol 4 are renewal points of the chain. Therefore, the blocks of symbols between successive occurrence of 4 are independent and identically distributed. Use these independent blocks to perform the usual F1's bootstrap procedure. We choose a sequence of blocks independently and uniformly with replacement, and the resample of size nj is obtained by the concatenation of the blocks we did this way, and you truncate this string obtained by concatenation at size nj. Now, the bootstrap procedure. For 2 different sample sizes, n1 smaller than n2 smaller than n, obtain B independent bootstrap resamples. So n is the size of the original sample. Denote this resample by x star bj t, where b is a number between 1 and b, and g is 1 and 2, and for g equal 1 and 2, and for all the champion trees tau n and its successor tau n prime, successor in the order we present a few slides before, we compute the average. So we see the average between the 2 log likelihoods. So we know that this difference is of the order of n before we get in the right context tree, and it is smaller than log of n after. So if you divide by n to the power 0.9, so this is very big before we get in the right context tree, until we get there, because it will be of order of n, the numerator, divided by something which is n to the power 0.9. But after we cross the correct champion tree, this will be very small, because the numerator will be smaller than log of nj, and it will be divided by nj to the power 0.9. So making the average, we are sure that you stabilize the result, and this is more or less the same thing as the expectation among all the possible resamples. Now we apply a test comparing the 2 statistics for 2 successive numbers, n1 and n2. In the criterion, select the smallest champion tree such that the test rejects the equality of the two statistics. Now, let's apply this to the linguistic data set. So we take 80 articles, we choose 20 articles for each year for each newspaper. At the end, we have around 1,100 symbols for BP and DP. And then we apply this criterion, and we got these two context trees. You see the difference is in the fact that in BP, the beginning, the syllable, which is the beginning of the prosodic words, is always a context in BP, but not in EP. What is common is that tree, which is beginning of a prosodic word, which is also a stressed syllable, is a context in both languages. But only in BP, the initial syllable of prosodic word is a context independently of being stressed or not. Okay, so at that point, we could ask me, are the linguists happy with this result? Is this coherent with the conjectures they had made before? The answer is yes, they are happy. I don't have time here to discuss the conjectures, but I invite you to read them in the article I quoted before. It's important to stress that to do our analysis, we don't use any linguistic information except the characteristic of stressed syllables and beginning of prosodic words. We did use ingredients associated to the conjectures. So the fact that we found trees that are coherent with former conjectures is a good point. So, conclusion. First of all, I must tell you that the fact that linguistic data appear as good candidate to stochastic modeling is not new. Markov himself had as original motivation the stochastic modeling of the poem Yevgeny Onegin from Pushkin. And he made a particular encoding of this poem to identify typical rhythmic patterns in this poem. Kolmogorov himself was interested on this. And there is this paper by Kolmogorov and Ryzhkov, which was reedited in 2000, which shows Kolmogorov doing this kind of analysis. But of course, nor Markov, neither Kolmogorov had the idea of using context tree models. This is something original of our paper. We believe that the interest of our approach goes far beyond its linguistic original motivation. I think that the smallest maximizing criterion is interesting by itself and should be used in many situations in which we have problems of turning the constant to identify the structure behind a sample of symbolic data. Thank you very much.